So in this video, we'll graduate beyond the domain of just vanilla binary search trees, like we've been talking about before, and we'll start talking about balanced binary search trees. These are the search trees you really want to use when you want to have real-time guarantees on your operation time, because they're search trees which are guaranteed to stay balanced, which means the height is guaranteed to stay logarithmic, which means all of the operations search trees support that we know and love will also be logarithmic in the number of keys that they're storing. So let's just quickly recap what is the basic search tree property. It should be the case that at every single node of your search tree, if you go to the left, you only see keys that are smaller than where you started, and if you go to the right, you only see keys that are bigger than where you started. And a really important observation, which is that given a set of keys, there are going to be lots and lots of different legitimate, valid binary search trees with those keys. So we've been having these running examples with the keys 1, 2, 3, 4, 5. On the one hand, you can have a nice and balanced search tree that has height only 2 with the keys 1 through 5. On the other hand, you can also have these crazy chains, basically devolved to linked lists, where the heights for n elements could be as high as n-1. So in general, you could have an exponential difference in the height. It could be as small in the best case as logarithmic, as big in the worst case as linear. So this obviously motivates search trees that have the additional property that you never have to worry about their height. You know they're going to be well balanced. You know they're going to have height logarithmic. You're never worried about them having this really lousy linear height. Remember why it's so important to have a small height. It's because the running time of all of the operations of search trees depends on the height. You want to do search, you want to do insertion, you want to find predecessors, whatever. The height is going to be what governs the running time of all of those properties. So the high-level idea behind balanced search trees is really exactly what you'd think, which is that, because the height can't be any better than logarithmic in the number of things you're storing, that's because the trees are binary, so the number of nodes can only double each level, so you need a logarithmic number of levels to accommodate everything that you're storing. But it's got to be logarithmic. Let's make sure it stays logarithmic all the time, even as we do insertions and deletions. If we can do that, then we get a very rich collection of supported operations all running in logarithmic time. As usual, n denotes the number of keys being stored in the tree. There are many, many, many different balanced search trees. Most of them are not super different from each other. I'm going to talk about one of the more popular ones, which are called red-black trees. So these were invented back in the 70s. These were not the first balanced binary search tree data structure. That honor belongs to AVL trees, which again are not very different from red-black trees, though the invariants are slightly different. Another thing you might want to look up and read about is a very cool data structure called splay trees due to Slater and Tarjan. Unlike red-black trees and AVL trees, which only are modified on insertions and deletions, which if you think about it is sort of what you'd expect, splay trees modify themselves even when you're doing lookups, even when you're doing searches. So they're sometimes called self-adjusting trees for that reason. And they're super simple, but they still have kind of amazing guarantees. And then finally, going beyond just the binary tree paradigm, many of you might want to look up examples of B trees or also B plus trees. These are very relevant for implementing databases. Here, what the idea is, in a given node, you're going to have not just one key, but many keys. And from a node, you have multiple branches that you can take, depending on where you're searching for falls with respect to the multiple keys that are at that node. The motivation in a database context for going beyond the binary paradigm is to have a better matchup with the memory hierarchy. So that's also very important, although a little bit outside of the scope here. That said, what we discuss about red-black trees, much of the intuition will translate to all of these other balanced tree data structures if you ever find yourself in a position where you need to learn more about them. So red-black trees are just the same as binary search trees, except they also always maintain a number of additional invariants. And so what I'm going to focus on in this video is, first of all, what the invariants are, and then how the invariants guarantee that the height will be logarithmic. Time permitting, at some point there'll be optional videos more about the guts, more about the implementations of red-black trees, namely how do you maintain these invariants under insertions and deletions. That's quite a bit more complicated, so that's appropriate for optional material. But understanding what the invariants are and what role they play in controlling the height is very accessible, and it's something I think every programmer should know. So I'm going to write down 4 invariants, and really the bite comes from the second 2, okay, from the third and the fourth invariants. The first 2 invariants, are just really cosmetic. So the first one we're going to store one bit of information additionally at each node beyond just the key. And we're going to call this bit as indicating whether it's a red or a black node. You might be wondering, why red-black? Well, I asked my colleague Leo Gibas about that a few years ago, and he told me that when he and Professor Sedgwick were writing up this article, the journals had access to a certain kind of new printing technology that allowed very limited color in the printed copies of the journals. And so they were eager to use it, and so they named their data structure red-black so they could have these nice red and black pictures in the journal article. Unfortunately, there was then some snafu, and at the end of the day, that technology wasn't actually available, so it wasn't actually printed the way they were envisioning it, but the name has stuck. So that's the rather idiosyncratic reason why these data structures got the name that they did, red-black trees. So secondly, we're going to maintain the invariant that the root of the search tree is always black, can never be red. Okay, so with the superficial pair of invariants out of the way, let's go to the two main ones. So first of all, we're never going to allow two reds in a row. By which I mean, if you have a red node in the search tree, then its children must be black. If you think about it for a second, you realize this also implies that if a node is red and it has a parent, then that parent has to be a black node. So in that sense, there are no two red nodes in a row anywhere in the tree. And the final invariant, which is also rather severe, is that every path you might take from root to a null pointer passes through exactly the same number of black nodes. So to be clear on what I mean by a root null path, what you should think about is an unsuccessful search. Right, so what happens in an unsuccessful search? You start at the root, depending on whether you need to get smaller or bigger. You go left or right respectively. You keep going left, right as appropriate until eventually you hit a null pointer. So I want you to think about that process by which you start at the root and then eventually fall off into the tree. In doing so, you traverse some number of nodes. Some of those nodes will be black, some of those nodes will be red. And I want you to keep track of the number of black nodes. And the constraints that a red-black tree by definition must satisfy is that no matter what path you take through the tree, starting from the root, terminating in a null pointer, the number of black nodes traversed has to be exactly the same. Cannot depend on the path, has to be exactly the same on every single root null path. Let's move on to some examples. So here's a claim, and this is meant to kind of whet your appetite for the idea that red-black trees must be pretty balanced. They have to have height basically logarithmic. So remember, what's the most unbalanced search tree? Well, that's these chains. So the claim is even a chain with 3 nodes cannot be a red-black tree. So what's the proof? Well, consider such a search tree. Right, so maybe with the key values 1, 2, and 3. So the question that we're asking is there a way to color these 3 nodes, red and black, so that all 4 of the invariants are satisfied? So we need to color each red or black. Remember, invariant 2 says the root, the 1, has to be black. So we have 4 possibilities for how to color 2 and 3. But really, because of the third invariant, we only have 3 possibilities. We can't color 2 and 3 both red, because then we'd have 2 reds in a row. So we can either make 2 red, 3 black, 2 black, 3 red, or both 2 and 3 black. And all of the cases are the same. Just to give one example, suppose that we colored the node 2 red, and 1 and 3 are black. The claim is invariant 4 is then broken. And invariant 4 is going to be broken no matter how we try and color 2 and 3 red and black. What does invariant 4 says? It says really on any unsuccessful search you pass through the same number of black nodes. And so one unsuccessful search would be you search for 0. And if you search for 0, you go to the root, you immediately go left and hit a null pointer, so you see exactly 1 black node, namely 1. On the other hand, suppose you searched for 4. Then you'd start at the root, you'd go right, you go to 2, you'd go right, you go to 3, you'd go right again, and only then would you hit a null pointer. And on that unsuccessful search, you'd encounter 2 black nodes, both the 1 and the 3. So that's a violation of the 4th invariant. Therefore, this would not be a red-black tree. I'll leave it for you to check that no matter how you try to color 2 and 3, red or black, you're going to break one of the invariants. If they're both red, you break the 3rd invariant. If at most one is red, you break the 4th invariant. So that's a non-example of a red-black tree. So let's look at an example of a red-black tree. A search tree where you actually can color the nodes red or black so that all 4 invariants are maintained. So one search tree which is very easy to make red-black is a perfectly balanced one. So for example, let's consider this 3-node search tree. It has the keys 3, 5, and 7, and let's suppose the 5 is the root. So it has one child on each side, the 3 and the 7. So can this be made a red-black tree? So remember what that question really means. It's asking, can we color these 3 nodes some combination of red and black so that all 4 of the invariants are satisfied? If you think about it a little bit, you realize, yeah, you can definitely color these nodes red or black to make and satisfy all 4 of the invariants. In particular, suppose we color all 3 of the nodes black. We've satisfied invariant number 1, we've colored all the nodes. We've satisfied invariant number 2, in particular the root is black. We've satisfied invariant number 3, there's no reds at all, so there's certainly no 2 reds in a row. And if you think about it, we satisfy invariant 4 because this tree is perfectly balanced. No matter what you unsuccessfully search for, you're going to encounter 2 black nodes. If you search for, say, 1, you're going to encounter 3 and 5. If you search for, say, 6, you're going to encounter 5 and 7. So all root null paths have exactly 2 black nodes. Invariant number 4 is also satisfied. So that's great. But of course, the whole point of having a binary search tree data structure is you want to be dynamic. You want to accommodate insertions and deletions. Every time you have an insertion or a deletion into a red-black tree, you get a new node. Let's say an insertion, you get a new node, you have to color it something, and now all of a sudden you got to worry about breaking one of these 4 invariants. So let me just show you some easy cases where you can accommodate insertions without too much work. Time permitting, we'll include some optional videos with the notion of rotations, which do more fundamental restructuring of search trees so that they can maintain the 4 invariants and stay nearly perfectly balanced. So if we have this red-black tree where everything's black and we insert, say, 6, that's going to get inserted down here. Now, if we try to color it black, it's no longer going to be a red-black tree. And that's because if we do an unsuccessful search now for, say, 5.5, we're going to encounter 3 black nodes, where if we do an unsuccessful search for 1, we only encounter 2 black nodes. So that's not going to work. But the way we can fix it is instead of coloring the 6 black, we color it red. And now this 6 is basically invisible to invariant number 4. It doesn't show up in any root null paths. So because you had 2 black nodes on all root null paths before the 6 was there, that's still true now that you have this red 6. So all 4 invariants are satisfied once you insert the 6 and color it red. If we then insert, say, an 8, we can pull exactly the same trick. We can color the 8 red. Again, it doesn't participate in invariant 4 at all, so we haven't broken it. Moreover, we still don't have 2 reds in a row, so we haven't broken invariant number 3 either. So this is yet another red-black tree. In fact, this is not the unique way to color the nodes of this search tree so that it satisfies all 4 of the invariants. If we instead recolor 6 and 8 black, but at the same time recolor the node 7 red, we're also golden. Clearly, the first 3 invariants are all satisfied, but also in pushing the red upward, consolidating the red at 6 and 8, and putting it at 7 instead, we haven't changed the number of black nodes on any given path. Any path that previously went through 6 went through 7. Anything that went through 8 went through 7. So there's exactly the same number of red and black nodes on each such path as there was before. So all paths still have equal number of black nodes, and invariant 4 remains satisfied. As I said, I've shown you here only very simple examples where you don't have to do much work on an insertion to retain the red-black properties. In general, if you keep inserting more and more stuff, and certainly if you do deletions, you have to work much harder to maintain those 4 invariants. Time permitting, we'll cover just a taste of it in some optional videos. So what's the point of these seemingly arbitrary 4 invariants of a red-black tree? Well, the whole point is that if you satisfy these 4 invariants in your search tree, then your height is going to be small. And because your height's going to be small, all your operations are going to be fast. So let me give you a proof that if a search tree satisfies the 4 invariants, then it has super small height. In fact, no more than double the absolute minimum it could conceivably have, at most 2 times log base 2 of n. So the formal claim is that every red-black tree with n nodes has height O of log n. More precisely, at most 2 times log base 2 of n plus 1. So here's the proof. And what's cool about this proof is it's very obvious the role played by these invariants 3 and 4. Essentially, what the invariants guarantee is that a red-black tree has to look like a perfectly balanced tree with, at most, a sort of factor 2 inflation. So let's see exactly what I mean. So let's begin with an observation. And this has nothing to do with red-black trees. Forget about the colors for a moment. And just think about the structure of binary trees. And let's suppose we have a lower bound on how long root null paths are in a tree. So for some parameter k, and go ahead and think of k as like 10 if you want. Suppose we have a tree where if you start from the root, and no matter how it is you navigate left and right child pointers until you terminate at a null pointer, no matter how you do it, you have no choice but to see at least k nodes along the way. If that hypothesis is satisfied, then, if you think about it, the top of this tree has to be totally filled in. So the top of this tree has to include a perfectly balanced search tree, binary tree, of depth k minus 1. So let me draw a picture here of the case of k equals 3. So if no matter how you go from the root to a null pointer, you have to see at least 3 nodes along the way, then it means the top 3 levels of this tree have to be full. So you have to have the root, it has to have both of its children, and it has to have all 4 of its grandchildren. The proof of this observation is by contradiction. If in fact you were missing some nodes in any of these top k levels, well, that would give you a way of hitting a null pointer seeing less than k nodes. So what's the point is? The point is this gives us a lower bound on the population of a search tree as a function of the length of its root null paths. So the size n of the tree must include at least the number of nodes in a perfectly balanced tree of depth k minus 1, which is 2 raised to the k minus 1. So for example, when k equals 3, it's 2 raised to the 3, 2 cubed, minus 1, or 7. So that's just a basic fact about trees, nothing about red-black trees. So let's now combine that with the red-black tree invariance to see why red-black trees have to have small height. So again, to recap where we got to on the previous slide, the size n, the number of nodes in a tree, is at least 2 to the k minus 1, where k is the fewest number of nodes you will ever see on a root null path. So let's rewrite this a little bit, and let's actually say, instead of having a lower bound on n in terms of k, let's have an upper bound on k in terms of n. So the length of every root null path, the minimum length of every root null path, is bounded above by log base 2 of quantity n plus 1. This is just adding 1 to both sides and taking the logarithm base 2. So what? What does this buy us? Well, now let's start thinking about red-black trees. So in a red-black tree with n nodes, what does this say? This says that the number of nodes, forget about red or black, just the number of nodes on some root null path has to be at most log base 2 of n plus 1. In the best case, all of those are black. Maybe some of them are red, but in the maximum case, all of them are black. So we can write in a red-black tree with n nodes, there is a root null path with at most log base 2 of n plus 1 black nodes. This is an even weaker statement than what we just proved. We proved that some path must have at most log base 2 of n plus 1 total nodes, so certainly that path has at most log base 2 of n plus 1 black nodes. Now let's apply the 2 knockout punches of our 2 invariants. Alright, so fundamentally, what is the fourth invariant telling us? It's telling us that if we look at a path in a red-black tree, we go from the root, we think about, say, an unsuccessful search, we go down to a null pointer. It says if we think of the red nodes as invisible, if we don't count them in our tally, then we're only going to see basically a logarithmic number of nodes. But when we care about the height of the red-black tree, of course, we care about all of the nodes, the red nodes and the black nodes. So far we know if we only count black nodes, then we're good. We only have log base 2 of n plus 1 nodes that we need to count. So here's where the third invariant comes in. It says, well, actually, black nodes are a majority of the nodes in the tree. In a strong sense, there are no 2 reds in a row on any path. So if we know the number of black nodes is small, then, because you can't have 2 reds in a row, the number of total nodes on the path is at most twice as large. In the worst case, you have a black root, then red, then black, then red, then black, then red, then black, etc. In the worst case, the number of red nodes is equal to the number of black nodes, which doubles the length of a path once you start counting the red nodes as well. And this is exactly what it means for a tree to have a logarithmic depth. So this, in fact, proves the claim. If a search tree satisfies the invariants 1 through 4, In particular, if there's no two reds in a row and all root and all paths have an equal number of black nodes, then knowing nothing else about this search tree, it's got to be almost balanced. It's perfectly balanced up to a factor of 2. And again, the point then is that operations in a search tree and the search trees are going to run in logarithmic time because the height is what governs the running time of those operations. Now, in some sense, I've only told you the easy part, which is if it just so happens that your search tree satisfies these four invariants, then you're good. The height is guaranteed to be small, so the operations are guaranteed to be fast. Clearly, that's exactly what you want from this data structure. But for the poor soul who has to actually implement this data structure, the hard work is maintaining these invariants even as the data structure changes. Remember, the point here is to be dynamic, to accommodate insertions and deletions. Insertions and deletions can disrupt these four invariants, and then one has to actually change the code to make sure they're satisfied again, so that the tree stays balanced, has low height, even under arbitrary sequences of insertions and deletions. So we're not going to cover that in this video. It can be done without significantly slowing down any of the operations. It's pretty tricky, takes some nice ideas. There's a couple well-known algorithms textbooks that cover those details, or if you look at open source implementations of balanced search trees, you can look at code that does that implementations. But because it can be done in a practical way, and because red-black trees support such a rich array of operations, that's why you will find them used in a number of practical applications. That's why balanced search trees should be part of your programmer toolbox.